This video is on the integration by substitution. So the role of substitution in integration is comparable to the role of chain rule in differentiation. And the key to use substitution is finding a piece of the function whose derivative is also in the function. The derivative is allowed to be off by a coefficient, but otherwise must appear in the function itself. So the procedure for using U substitution is first look for a piece of the function whose derivative is also in the function. If you're not sure what to use, try the denominator or something being raised to a power in the function. 2. Set u equal to that piece of the function and take the derivative with respect to nothing. And 3. Use your u and du expressions to replace parts of the original integral, and your new integral will be much easier to solve. This bottom box is practically saying the same as this top box here, so I'm not going to go through this one. But pattern recognition when looking at integrals. If you're given an integral and you have an outside function and an inside function, but also within the integral you have the derivative of the inside function, then you would use U substitution. So let's go through some examples. I have written the answers for the first 5 for example 1 so that you can try those on your own. I'm going to go through the last 5 examples simply because usually the last 5 examples are the harder ones. So starting with letter F. We've got some form of chain rule here, so we're going to use U substitution. We're going to let U equal the inner part of the radical, which is going to be 7 minus 2x cubed. Then we're going to take the derivative of that, which would be negative 6x squared dx. Well, within our integral, we have the x squared dx part, but we don't have that negative 6. So what we're going to do is we're going to divide du by negative 6 so that we get du over negative 6 is equal to x squared dx. The reason we do that is because when we rewrite the integral, we'll have, and I'm going to write that as a rational exponent, u to the 4/3 du divided by negative 6. U was the parentheses part, 4/3 was just rewriting the radical. Du over negative 6 is equal to the x squared dx portion. Well, now from here I can pull out a negative 1/6 because that's a constant. So I have the integral u to the 4/3 du, and then I would just use power rule to integrate that. So it'd be negative 1/6 u to the 7/3 divided by 7/3 plus c, which then simplifies to negative 3 over 42 u to the 7/3 plus c. At this point, there's nothing else I can do other than replace u with what we had originally pulled out for u. So this simplifies to negative 1 over 14. U is 7 minus 2x cubed to the 7/3 plus c. And that would be our answer. Another example. Here, we're going to let u be the 3x part. Take the derivative, which would be 3 dx, which are both within my integral. So we rewrite that to be cosine of u du. We integrate, and that's sine of u plus c. There's nothing further I can do other than replace u. So sine 3x plus c is the final answer. Here, same thing. U will be 10x du would be 10 dx. However, in the original integral, I only have dx, so I divide both sides by 10. So we get du over 10 is equal to dx. Rewrite our integral. So that's the integral of sine u times du over 10. Pull out the constant, which is 1/10. Integral of sine u du. Integrate it, which gives you negative 1/10 cosine u plus c. And that's just negative 1/10 cosine 10x plus c. Here we're going to let u equal to 1 minus 4x. du is negative 4 dx. Within the original one, we only have the dx portion, so divide by negative 1/4. Rewrite the integral, so it's secant squared u times du over negative 1/4. Just as in the previous examples, pull out the constant. Secant squared u du, integrate it, which would then give us negative 1/4 tangent of u plus c, which then equals negative 1/4 tangent of 1 minus 4x plus c. And that would be our answer for this one. And the last example, we're going to let u equal cosine of x. The derivative of cosine is negative sine x dx. Sine x dx is in there, but the negative portion isn't, so we divide both sides by a negative 1. We rewrite the integral to be the integral of u to the 4th times du divided by a negative 1. Pull out the constant. Negative 1 u to the 4th du. Integrate it. That's negative u to the 5th over 5 plus c. When we rewrite it, it's negative 1/5 cosine x to the 5th plus c. Now, that's when we're not given any limits. If we are given limits, and then this is going over the general power rule for integration, which we already know how to use. You add 1, divide by the new exponent. But change of variables for definite integrals. When using u substitution with a definite integral, it is convenient to determine the limits of integration for the variable u rather than to convert the antiderivative back to the variable x and evaluate at the original limits. And then this bottom box is saying the same thing as this, change of variables for definite integrals. So let me just give you the solution to part A, which you'll work out on your own. Make sure that you get this, 52/3 as your final answer. You have to use u substitution first, but let me go through example B, and that'll help you to answer part A. So before anything, we have to find u, which in this case is going to be cosine 2 theta. The derivative of this is we have to use chain rule, which would be negative 2 sine of 2 theta d theta. Well, in the original integral, we have sine 2 theta d theta, which is this portion of our derivative. So we're going to divide both sides by a negative 2. Now, before we rewrite anything, we're going to change our limits here. These limits were in terms of theta. We're now going to rewrite them in terms of u. So what we're going to do is when